Okay, so we're going to do another induction proof. And so our theorem is that the sum of k equals 0 to n of 3 to the k is equal to the closed form of 3 to the n plus 1 minus 1 over 2. And so this is for all that upside down a non-negative. So we're going to say first proof by mathematical induction on n. And then we're going to do the basis. So remember, the basis is we're going to pick the easiest term. So we're going to make the sum just have one element, all right? And we're going to see if it works for just one element. So the first term in the sum. So we're going to say for, so this should be k equals 0 and to n equals 0, right? That's the first term. Let's see if I can get my pen to work. Of 3 to the k. Does that equal the closed form, this closed form, for when n equals 0? So this is going to be 3 to the 0 plus 1 minus 1 over 2. Is that true? Well, what is the first term then? The first term is just plugging in 3 to the 0, right? That's if I take this sum and I only have one term, the only term is going to be the k equals 0 to n equals 0, so it's just 3 to the 0. Does that equal 3 to the 0 plus 1 is just 3 to the 1 minus 3, or sorry, minus 1. Let me erase that. Minus 1 over 2. So is that true? Well, 3 to the 0 is 1, and does that equal 3 to the 1 is 3, minus 1 is 2, and so 2 over 2 is equal to 1. So we have 1 is equal to 1. So that works. So we have our base case. We're just looking at the sum, and the sum only has one term in it, and it works for the closed form. So the next thing we need to do is we need to do the induction step. I guess we need to do the induction hypothesis. So here we assume that the sum from k equals 0 to n of 3 to the k is equal to 3 to the n plus 1 minus 1 over 2. So that's our assumption. And then our step, so our induction step, we must show that the sum to n plus 1, so we're saying all of the terms that we had for our induction hypothesis, all of those terms to n, we're going to say, well, we are going to assume that it works for any if we can add another term to our sum and it works. 3 to the k. And so we're going to say that this is equal to 3 to the n plus 1, right? I'm taking this, and that's taking this, and I'm plugging it in right here. So here it just went to n, and now I'm saying it goes to n plus 1, so it's n plus 1 minus 1 over 2. And so that's what we wanted to show. Is that actually true? Well, we're going to do that little trick where this is equal to, so the sum of n plus 2n plus 1 of k equals 0 to 3 to the k. That's equal to the sum when we just go to n, k equals 0, of 3 to the k, plus the next term. And so the next term is just 3 to the n plus 1. Right, so we know that. And then what I'm going to do is I'm going to take this and plug it in up here for that term, and then set this thing equal to the closed form, this, and see if it works. And if it does, then I've shown that that this proof works for all non-negative integers. So plugging this in, I get 3. 10. Right, so n, k equals 0, 3 to the k, plus 3 to the n plus 1. And does that equal 3 to the n plus 1 minus 1 over 2? So remember now, for this piece right here, I'm going to go back up and plug in this right here. So this is my closed form, and I'm assuming that that's true. So I'm going to plug this closed form in down here for this piece. So this is going to be 3 to the n plus 1 minus 1 over 2 plus 3 to the n plus 1. Does it equal 3 to the n plus 1 minus 1 over 2? Is that true? So here I can say that I have 3 to the n plus 1 over 2 minus 1/2, right? I'm just saying taking half of this and half of the 3 to the n plus 1 and then half of the 1/2. So plus 3 to the n plus 1. Does it equal 3 to the n plus 1 plus 1 minus 2? And so if I can see that these are similar, so I'm going to get a common denominator. So I'm going to have 3 to the n plus 1 over 2 plus, now 3 to the n plus 1 over 2 is just like 2 over 2 times 3 to the n plus 1, and then minus 1/2. Does it equal, I forgot, wrote this wrong, minus 1 over 2. So 3 to the n plus 1 plus 1 minus 1 over 2. Okay, so here I have this common denominator, so I have a half and then a whole, so this is going to be 3 times 3 to the n plus 1 over 2 minus 1/2. And so I have this 3 times 3 to the n plus 1. And so again, I'm questioning this. 3 to the n plus 1 minus 1 over 2. Okay, so 3 times 3 to the n plus 1 is really 3 to the n plus 2. Oops. Right, so I'm just adding another term up here to this one, and over 2, and since it's the common denominator, I get 3 to the n plus 2 minus 1 over 2, and that's equal to 3 to the n plus 2 over here minus 1 over 2. So these two are equal, and I've shown that my proof works. My proof is true.